a question regarding the first catalyst that you talked about, the CO.
Yeah.
And you showed the bilayers of the gold. And actually, can you show or have you already seen that there is a selective deposition or layer formation of different substrate surfaces for the iron? Or have you actually been able to see if this is preferentially on different crystal segments?
No, not at the moment. We just use the catalyst as they're made, as the co-precipitation produces a wide range of species. We haven't gone to the basis of the support yet.
Nice work.
Thank you, speaker, once again.
Let's see, I guess we're starting back at 1:30.
Second of 6 sessions in honor of Bert Davis, the recipient of the ACS Distinguished Researcher Award. And before we go into the first talk, I would like to just quickly one more time reiterate what I said this morning about the special dinner. All speakers are invited, and also the special invited guests, to come and join us for a dinner at the Marriott. And this dinner is sponsored by the Center for Applied Energy Research at the University of Kentucky. And we will start at 7 o'clock with the reception, and then 7:30 dinner and presentation on some of the interviews that Bert has taken over the years, some very exciting slideshows that Gary has put together. So we're looking forward to that very much. One more thing, if you would please see either Gary or myself for the tickets, that would be great. Thank you. So let's start with the afternoon session, and it is my great pleasure to introduce Professor Krijn de Jong. He is the scientific director at the Dubai Institute for Nanomaterials Science at the University of Utrecht. And for 15 years he was with Shell Research, working on catalyst synthesis, heavy oil conversion, environmental processes, zeolite catalysis, and synthetic gas production and conversion. And he was appointed as full professor in 1997 at the University of Utrecht. He has received a number of Shell and patent awards in 1987 and 1991. And just very recently he gave a brilliant talk in Doha about a month ago when he was the recipient of this year's Natural Gas Conversion Board's Award for Excellence. The title of his presentation will be Supported Iron and Cobalt Catalyst, Nanoparticles for Fischer-Tropsch Catalysts. Would you please help me welcome Professor Krijn de Jong?
Thank you very much for this very kind introduction. Ladies and gentlemen, I would like to start off with thanking the organizers for putting together such an excellent symposium, and also a great festivity, I think, to honor Dr. Bertrand Davis for his eminent contributions to a broad field of catalysis. And I think for many of us it's a pleasure to be here together as friends and colleagues, and we would like to congratulate you on behalf of this occasion and in receiving this prestigious award. In talking about the topic indicated, Fischer-Tropsch catalysis is a topic close to Bert's heart, I might say. And just to underline that from Web of Science, it makes us modest if we note the number of publications, and I just took, let's say roughly speaking, the last 2 decades, the number of publications on the one hand on iron Fischer-Tropsch catalyst, on the other hand on cobalt Fischer-Tropsch catalyst, and in some years, for example in 2011, I think in total iron and cobalt together he published more papers on Fischer-Tropsch than many of us throughout our career. So that makes us modest in view of his great contributions, not only in quantity but also in quality. I think he inspired many of us to realize the important features of cobalt catalyst deactivation, for example, iron carburization and the impact on mechanical stability, and so on and so forth. So today I would like to build upon that and talk about iron and cobalt for physitropic catalysis. First of all, with introducing the topic, and then moving to cobalt and briefly to iron. Synthesis gas conversion, it has been said also this morning, is versatile in the sense that the synthesis gas, a mixture of CO and hydrogen, can be produced from a wide variety of feedstocks and give us a wide variety of products. If you go for cobalt catalyst, we will make mainly alkanes as products and water. In the case of iron, alkenes and CO2. Well, in the career of Dr. Davis, it was clear that his main effort in the early 90s was on iron, and later on, more or less, he shifted to cobalt. I will do the other way around and discuss first cobalt and later on something on iron. Supported metal nanoparticles will be the focus of this talk. So let's briefly introduce that topic, realizing that in a macroporous support body, millimeter size for fixed bed or micrometer size, tens of microns for slurry bed or fluid bed catalysis, we can zoom in and realize that we have support particles, let's say some tens of nanometers, and dispersed on that support particles, let's say in the size range 1 to 20 nanometers. And if we consider metal nanoparticles, we need to consider individual properties, and today I will touch not on all of these properties, but I will mention something on composition, size, and support. In particular for the cobalt, we will dwell a bit on that topic of the support influences. On the other hand, next to, you might say, individual properties, we also consider what I like to call collective properties. So the behavior of a large ensemble of nanoparticles, which has impact on a number of parameters, but for this talk I will mainly focus on the distribution of nanoparticles over the support. And to illustrate what I'm hinting at is here a TEM image of a silica support. This is 50 nanometers, the scale bar. So the primary silicon particles are about 20 nanometers or so, and I dispersed or have drawn about 50 nanoparticles dispersed over this area of the support in three fundamentally different ways. One is what I call high density domains of nanoparticles. One is clusters where the particles interact directly with each other, and uniform distributions of nanoparticles. And this has an impact, and we will discuss this for cobalt and also for iron, how this affects the performance of these catalysts. We need a few research tools in order to be able to contribute at a fundamental level to this field, and just briefly highlighting those research tools. So we use the synthesis method of impregnation and drying, and this morning we learned we can use metal clusters and many other techniques, but still I think it's fair to say that this is a very important technique, and to understand that at a fundamental level is one of our thrusts. So we discriminate between impregnation of the solution onto the support, then drying to evaporate the solvent, which gives us the supported metal salt, for example nickel nitrate in this case, and after calcination or thermal treatment we get metal oxide particles on our support, and after reduction we observe the metal nanoparticles. And also I should emphasize that the group of Dr. Davis has contributed a lot to the understanding, for example, of the reduction step and the addition of noble metal promoters. I won't go into that specifically, but mainly talk about the drying step and the effects of that on the performance and the distribution of the nanoparticles. We use model supports, for example, ordered mesoporous silica like MCM41 and SBA15, with the mesopores well ordered with respect to each other. In this case, SBA15 with 9 nanometer pores is something that assists us to derive fundamental relationships, you might say synthesis, structure, performance relationships. Electron tomography is in our toolbox to derive, and again that was introduced this morning, this problem if you have a cluster of nanoparticles and we have a transmission electron microscope, the electron beam will go through the cluster and we will observe a projection of that cluster, which makes it very difficult to derive quantitative data of particle-particle distances from this projection. So what we do is multiple projections, thereby fill up the, after Fourier transformation, the three-dimensional Fourier space, and inverse Fourier transformation gives us the possibility to numerically calculate the three-dimensional object. And the fourth one is, of course, catalysis. We need catalysis. This is from Avantium, a so-called Florence unit, with these typical conditions, up to 550 degrees centigrade at 80 bar, also with syngas and online GC analysis. The 16 parallel reactors are in 4 blocks that we can heat independently, so we can select 4 different temperatures, but within one block the temperature is uniform. So that's about the tools. Now let's move to cobalt. And for cobalt, we have studied the following phenomena that I would briefly like to highlight with you. We will study the effect of aggregation of cobalt particles in cobalt silica systems, then the effect of the synthesis method on the performance of titanium-supported cobalt catalysts, and finally something on niobium-supported cobalt catalysts. Well, the catalyst preparation that we used in case of the silica support was that we first started with a model support, an SPA 15, so the ordered mesoporous materials with this given pore volume and pore diameter of 9 nanometers. And we use an incipient wetness impregnation technique with a concentrated cobalt nitrate solution. I will focus after the drying step, where we apply cryo-electron tomography in order to prevent decomposition of the cobalt nitrate in the electron beam. We heard also about beam damage this morning. One way to prevent it is to cool your sample to 77 Kelvin in the electron microscope. And the dried sample we will study with electron tomography. So we will jump, and I will not go into these details. I will use another support for that, but just to highlight the impact of drying on the distribution of metal nanoparticles in supported catalysts. Here is the structure of the system. So this is an SBA 15 particle, in this case with the electron beam parallel to the pores. In this case, the electron beam perpendicular to the pores, but this is from one and the same electron tomogram. So what we will do, and I will start the movie now, we will travel through this particle with the mesopores in this direction, and every position of the bar we see an orthogonal cross cut from the electron tomogram in the SPA50 particle. And what we clearly can see is that some bright spots are there, and the bright spots essentially are empty pores. But we also have uniform gray areas over a number of pores, and those are heavily loaded with cobalt nitrate. So clearly what we observe is that the cobalt nitrate has been deposited as plugs, nano plugs you might say, or nano rods of cobalt nitrate over a number of pores, while other pores are empty over large distances. You can also see it here. This is an empty pore, these are filled pores. We can prevent that because this is after conventional drying, 60 degrees centigrade. Typically we dry, and then we get this patch-wise or plug-wise deposition. If we carry out freeze drying, so we cool the sample to liquid nitrogen temperature, slowly heat it up, then we get a very uniform distribution of our cobalt nitrate. So clearly we can prevent the problem, but it's cumbersome, of course. Freeze drying is technically not so difficult, but it takes a long time. So what we did is that Tamara Eggenhuizen was working on this model support and used the freeze drying. That another PhD student, Peter Bunnik, started to work with the industrial silica gel support and vary the drying temperature, but perhaps even more importantly, the hydrodynamics of the system. He moved from stagnant drying, what is usually in laboratory, at laboratory scale, people impregnate a catalyst, put it in a muffled furnace, come back the next day, and take it out. That's the drying in many, many cases. Well, we use the fluid bed, so that controls more, gets you more uniform conditions for each individual macroscopic particle. And then they measure the Fischer-Tropsch catalysis at 20 bar. So let's first have a look. We need, because it's now in a silicate gel, we need an ultramicrotome sections in order to be able to get good images. And that is what we observe here. We see the different conditions. The scale bar in all cases is 250 nanometers. And this is not a single particle, but rather it is a cluster of many, many hundreds of nanoparticles. In all cases, the CO3O4 crystallite size is about 10 nanometers. So there's no variation in crystallite size at this stage of the drying and calcination in this case. But it is rather a distribution in aggregate size. So these are huge aggregates of about 200 nanometers. This is about 50 nanometers, 20 nanometers, and then in this case the aggregate size is close to the particle size. Sometimes we have a few particles together, but many of them are isolated. So we can control the aggregate size, and the question is, what is the impact on catalysis? Well, I'll jump straight away to the results because time is short. So here are the conditions: 20 bar, 240 degrees C, etc. CO conversions vary between 30 and 50%. And this is the weight time yield. So while the cobalt loading is the same, it is expressed per gram of catalyst. And what we see as a function of time is that there's a significant variation of both the initial and the almost steady state activity after some 200 hours. And clearly, with the isolated nanoparticles, you get significantly higher activities compared to the very large aggregates. Well, since we applied a quite severe reduction, this may be an impact via the reduction rather than the catalysis. However, it also seems that the most significant deactivations are apparent with the catalyst with the lowest activity. And that's something that intrigues us, and therefore we study now more extensively the deactivation behavior of these different systems. Of course, in FT, C5 plus selectivity is key. We don't want the methane, often we don't want the C2, C4. We prefer the liquid products, and the liquid products are C5 plus. So this is C5 plus selectivity from 72 to 82%, plotted here as a function of this aggregate size. And there seems to be a rough correlation with aggregate size, although some people may say a horizontal line will do as well. But the points that deviate are either because of very high conversion in this case, or low conversion because of the lower activity of the large aggregates. So we have to work this out further, but it reminds us, on the one hand, this conversion effect, of course, is known. For example, very recently, Remy Bourcourt has published about that. But another one that's very important, and the Holman group has published that a few years ago, that if these aggregate sizes, or then they refer to the primary particle sizes, were larger, that the C5 plus selectivity went up. And what we noted is that the olefin to paraffin ratio that's plotted on the right-hand axis increases with aggregate size. It seems to be that we have a more olefinic product in the case of larger aggregates, and of course that may give rise to secondary reactions and higher C5 plus selectivity. Clearly more work is needed, but I think the observations are very intriguing. Titania is an important support these days, studied a lot, and what we did, we were interested in the method of synthesis, or the method of depositing the cobalt onto the titania. We took a classic P25 titania from Evonik, formerly Degussa, and we either deposited via ammonia deposition precipitation, or urea, or the incipient wetness impregnation. Of course, we characterized. Time is lacking to go into all the characterization details, so I'll jump straight away to the catalytic testing using these abbreviations of the ammonia, the urea, and the impregnation methods for the cobalt titania catalysts. First of all, the activity, the cobalt time yield, now plotted per gram of cobalt, the activity as a function of cobalt loading. Here are the conditions. There's some variation in conversion. I think the maximum was about 20 to 40% CO conversion. And what we observe is that there's a clear advantage of this ammonia precipitation method, which has been patented by Johnson Matthey. Martin Locke was one of the inventors of that, where it's clear that at intermediate loadings is a great benefit, probably through dispersion. From our characterization, it's mainly a dispersion effect. When we go to high loadings, it more or less converges, more or less gets independent of the method we use. Surprisingly, the C5 plus selectivity, and this should be in weight percent, the C5 plus selectivity consistently is significantly higher for the HDA catalyst. Partly because of a conversion effect, but the conversion effect is much smaller than this very significant effect that we measure for this series of catalysts. So this is for us now a topic of study. What's going on? It's cobalt and titania, no promoter, no. There are dispersion differences, but higher dispersions usually give you lower C5 plus selectivity, also studied by the Holman group in the past. And I think it's not straightforward to assign this to a dispersion. So it may be distribution, it may be something, the activation of the titania. That's something that we are currently studying. Last topic for cobalt is niobium-supported cobalt catalyst. We had some interesting observations with niobium. It builds upon earlier work at University of Rio de Janeiro. Richard Small and others have studied that quite some time ago to use niobium as a support, and what they found that you need to have crystalline niobium. The amorphous niobium gives you low activities, so we followed that work and carried out the crystallization of niobium at elevated temperatures, which implies you have a low surface area support, which seems a poor proposition for an FT catalyst, and usually you require high metal loadings. And of course you can achieve high metal loading by multiple impregnations, but still the dispersion of the cobalt will go down. And to illustrate that problem, if you have 11 weight percent of cobalt, this is the niobium particles, quite large, something like 100 nanometers in size, and here are clustered cobalt particles that are, of course, I think this Stu Solus has once called them graveyards for catalysis. And so that's not a very good proposition. So what we did, we stuck with, we choose to go for 5 weight percent cobalt to prevent this agglomeration of the cobalt nanoparticles. If we then plot the weight time yield, so per gram of catalyst, as a function of temperature, the cobalt niobium with 5% cobalt, of course, has no chance to compete with 25 weight percent of cobalt on gamma alumina. More the, let's say, the classical gamma alumina supported cobalt catalysts that have been studied so much also by Bertrand Davis and his group. The activity is way higher. There's a plateau because of the very high CO conversion that we achieve at the highest temperatures. Again, it's not only activity, it is selectivity. So if we plot here the selectivity, there's methane on the one hand and C5 plus on the other. And consistently, the C5 plus selectivity of cobalt on niobium is much higher is much higher than the C5 plus selectivity on gamma alumina. And our proposal is to harvest that high selectivity in the sense that if you put a certain target, let's say around 80% or so, you can run the cobalt niobium catalyst at much higher temperatures than you can operate the cobalt on gamma alumina. And that's summarized in this plot. So if we take now the weight time yield, so per gram of catalyst on the vertical axis, and the C5 plus on the horizontal, and we take 80% as a target, you see that both catalysts more or less give the same weight time yield. In other words, I can operate cobalt niobium at higher temperatures, thereby compensate for the lower metal loadings. That was what I wanted to say about cobalt. Since Bert extensively contributed to iron Fischer-Tropsch catalysis, I found it worthwhile to also include a little bit of our work that was to a significant extent inspired by his work, because he showed so well, working also with Datei and others, that cobalt carbide suffers from mechanical disintegration. So what we wanted to do is move to supported iron particles. So the support was a key aspect of our work. The promoters, the particle size, the iron nanoparticle spacing, it was all there. And we applied it for so-called physiotropes to olefins. Esa Torres and Art Koeken have been contributing and doing this work. Again, a variety of feedstocks. We make syngas, and if you want to go to lower olefins these days, we go either via methanol, as practiced now in China, or we go via FT, the FT naphtha fraction in particular, because it makes poor gasoline. So that's fantastic steam cracker feedstock. So this is both an operation, and this could be an alternative. So we were studying this direct conversion of syngas to C2 to C4 lower olefins. It's a long story, and I've only 5 minutes to go, so I'll summarize it by saying that it's an integrated approach by the support selection, the fact that we must prevent aggregation of the iron nanoparticles. I will highlight this point in particular. Control the iron particle size, but also the promoters. And this ends up in a catalyst where we have an alpha alumina particle of, let's say, 100 nanometers or more, and we have iron nanoparticles of 10 to 20 nanometers dispersed over the alpha alumina. The iron particles are promoted by sodium and sulfur. I won't go into that, but those promoters are essentially to suppress the methane formation at the elevated temperatures that we apply. And to first then discuss the support effect, then the size effect, and then the aggregation. Well, the support effect in one plot, so if we have the product selectivity, our enemy is methane because we operate, in this case, at 340 degrees centigrade, 20 bar, 340 degrees centigrade, and a hydrogen CO ratio of 1, very severe conditions and very high CO conversions for these active catalysts. The product selectivity as a function of the catalyst activity per gram of iron. With this conventional support, our problem is twofold. We have low activity and we make lots of methane. Moving to a support like alpha alumina, carbon nanofibers, carbon nanotubes, as has been published recently by Martin Muller and his group, are give much more active catalysts, but also drive down the methane and enhance the green points, what are the selectivity to lower olefins of the hydrocarbons produced. The iron carbide particle size is very important. If we estimate or calculate a turnover frequency, which is much more difficult with iron, I would say, than with cobalt, or it's much less straightforward. But still, in an effort to do that, we have these numbers on the vertical axis and the iron carbide particle size. Using carbon nanofibers as support material, we observe an overall increase of the turnover frequency with decrease in particle size. This is very much inverse of what we observe with cobalt. With cobalt it goes down, now it goes up. However, it goes only up for the methane. The methane turnover frequency, as indicated here, goes up steeply, while the turnover frequency for C2 plus products is constant. So it's a clear design parameter, you might say. We want particles that are sufficiently large in order to prevent the contribution of more methane than necessary, you might say. Finally, the distribution, the effects of the nanoparticle distribution. Again, our alpha alumina support with particles 100 to 200 nanometers, so typical specific surface area of about 10 square meters per gram. If we impregnate iron nitrate, we observe alpha alumina particles that give a very smooth appearance. That implies there's hardly any iron oxide particles present on that support particle. On the other hand, this support particle is heavily loaded with iron oxide, as was also confirmed by EDX. If we use ammonium iron citrate as a precursor, which has a completely different impregnation, drying, etc. behavior, we see that we get very nice distributions of our iron nanoparticles over the support, much more uniform than in the case of the iron nitrate. Now what we did in a so-called tapered element oscillating microbalance, where we have the possibility to operate at 20 bar under real plug flow conditions, so we have a catalyst bed in a hollow rod, and the synthesis gas can flow through the catalyst bed under plug flow conditions. We can measure very accurately the mass of our sample under a full catalysis experiment. We have published this recently to be applied for FTO. Again, I have to mention here the work of Du Chen and Anders Holman, who did extensive carbon growth studies, you might say carbon nanofiber growth studies on nickel catalysts with such a system. If we measure now under full FTO conditions, here are the conditions: 350 degrees centigrade, 20 bar, CO-rich synthesis gas. We used very high space velocity to prevent any condensation of products. That's of course important because you always make C5 plus products under FTO conditions. And admittedly a short period of time. But still in this short period of time, with iron nitrate catalysts, so same loading, same iron oxide nanoparticle precursor size of about 20-25 nanometers, a much faster uptake of coke, so this is the amount of carbon, so already something like 15 to 20 weight% of carbon after 6 hours on stream, while the ammonium iron citrate with this distribution of nanoparticles gives us a much or substantially less carbon deposited after these 6 hours on stream. So this is the best catalyst we have now. This is the alpha lumina, this is the electron tomogram, but still we see that we have quite some clustered particles and not only isolated particles, and that may be the reason that we still pick up coke or nucleate carbon filaments on these clustered particles. That's a future research topic now for us. So the cobalt work, the drying method is very important for the cobalt distribution, which affect activity and selectivity, perhaps even stability. Cobalt on titania, we see a tremendous effect on the synthesis method. There's a great surprise, more than what dispersion effects can explain as yet. And niobium seems to be an interesting support to operate, in particular at high temperatures. Iron we discussed, support, size, and promoter effects, and also the distribution of the nanoparticles. Model supports are important in our work. I think we can learn from those and translate, like the silicon, to industrial supports. The electron tomography is a powerful tool, in particular if you want to study distribution effects. And with that, I think that synthesis studies, the synthesis of catalyst gives us new avenues for synthesis gas catalysis. A lot of acknowledgements for funding, the people involved. Our group, 2 years ago, we moved to this laboratory, and I think for a final shot of the video that is being recorded, I thought that this was a nice end. Although now you're focusing at me, I get a bit nervous. Thank you for switching back to the building. It was really a pleasure, Bert, to see you at so many occasions, also at this one. And ladies and gentlemen, thank you for your kind attention.
Thank you very much for this wonderful presentation, and the floor is open for questions. Okay.
These are nice interrelations now to the particle size, but finally the chemistry is on the surface. So I feel there's still a little gap in between, yes, to understand the science, active science, and what's happening in the particles themselves. So I wonder, there's a beautiful picture image from Shell, seeing the structure of the segregated over. Is something in that direction?
Yeah, absolutely. I fully agree. So the catalysis is at the surface. That's the reason with the cobalt that we did extensive SITCA work, because then you measure residence times and coverages of the active species, which are clearly a function of size. And that's exactly what we are now doing also with the iron carbide, to sort out what's the difference at the surface as a function of size, because you're absolutely right.
Yes. Last row.
Okay. So, there was a paper which reported the carbon weaknesses on the iron carbide. They could be exercised. Do you have some comments? That, there are some early evidence or something?
Not yet, because at this stage what we did was first collect the data, which is already difficult enough to vary the particle size. It's very challenging from a synthesis point of view, narrow particle size distributions and so on and so forth. But you're absolutely right, building on the question of Professor Schultz, that the surface structure is what counts. So you may be right that vacancies and other structural features are different at different particle sizes. Thank you.
When you move from gamma lumen to alpha lumen, you have a loss of surface area of the order of 100 or something. How does this how is this taken into account? What is the contribution of the high surface area of gamma lumen, if any?
Yeah, what we investigated extensively, that with the high surface area supports, essentially what happens is the interaction of the iron oxide with the, in this case, gamma lumina or silica is so strong that the carburization that is needed to activate the catalyst does not take place. So we did Nussbauer spectroscopy, and essentially even at 20 bar, 350 degrees centigrade, 20 bar of syngas, you do not proceed towards the active phase.
I think that it is related to that. So if you would use not MCM for the 1 or SPA 15, but if you had ordered mesoporous zeolites, for example, what would be the impact of that? So you have more active support and more acidic support. How would this?
For the iron?
For the cobalt.
Oh, for the cobalt?
Yes, no.
I'm not sure whether you're hinting at secondary reactions to correct the waxes, or is it?
I'm not sure how this would affect the distribution probably of the nanoparticles or the activity of the catalyst to go to the primary reactions actually.
Right. Well, we didn't study that, so it's a good question. Mesoporous zeolites are, of course, studied a lot these days. But in general, with the very reactive surface that these mesoporous zeolites provide still with the silica, alumina, etc., with, let's say, 10 or 20 bar steam in the reactor,
right.
I think that the de-illumination, all the processes would go on under these conditions.
Because of time, we probably won't have more questions at this time, but we may be able to have more questions tonight at dinner. So if you would please help me again, thank Dr. Krijn de Jong for this wonderful presentation.